Hello, everyone. Have you ever been listening to a song and thought, man, I wonder what this song's dominant frequency is? Yeah, me too. So I'm going to show you a little demo of that in deconstructing and filtering an audio wave. The tools I'm going to be using are Audacity and JupyterLab Notebook. Here's a simple signal flow diagram of how the code is going to be sampled and processed and filtered. So first, our sampled wave. That comes in as a .wav file, and that .wav file is read uh, read into an array in Python. Using Python's capabilities, we can find the length, sample rate, and period. And those are all things that we need in order to conduct the FFT on it, the fast Fourier transform on our points. The fast Fourier transform takes our points and puts it into the frequency domain. Now we have our frequency spectrum at this point right here. And with that, we can see exactly what frequencies are present in our wave. Using a simple filter, and what this filter will do is any number, any frequency that has a weighting less than a certain threshold, we're just going to discard those and leave only the frequencies that we want. And I'll show you exactly what that means in just a little bit. So now that we have our modified frequency values, we can do the inverse FFT and move back into the time domain and graph it. And that'll give us our wave that we should have isolated and the wave that we want. So moving on to the coding portion, the JupyterLab portion. All right, here we are. Let's listen to what it sounds like. Just a simple E string of a guitar, and here is the total response of the guitar, and this is a zoomed in response of the guitar. As you can see, there's definitely a periodic waveform here, but you can't pinpoint exactly what frequency it is because of all the other frequencies that are added in the mix. So let's do the FFT and graph that. And here's a frequency spectrum of the guitar string. We can already see that here on the left are the positive frequencies, and here on the right are the negative frequencies. This is the shifted graph, so everything has been moved half the sample rate. I'm going to take a look at just the first half here in the next graph, and using the filtering method that I was talking about, I'm going to take out any frequencies that have a power spectral density less than a certain amount. So here you can see just that. The power spectrum density cutoff that I picked is 400, and we can see that anything below this number cuts off and goes to 0. So now that we have that, we can zoom in and see exactly what frequency is present. And we can see that a guitar E string has a dominant frequency of about 330 hertz or so. And that's interesting to see. And here is the time response of the guitar E string. So, but what does this really mean? Well, to be honest, this doesn't really mean much because we essentially took a guitar E string and deconstructed it. So it is no longer a guitar E string anymore. It is just a simple wave at this point. But let's put this into practice, into something that is much more useful, where we have a wave that we want to listen into the background, but a lot of noise is obstructing it. And I'm going to demonstrate in the next demo. Here we are. Let's play the file. So that audio file had a lot of noise, and we can see here in the zoomed in time response of the wave. Looks very jagged, not really sure what type of frequency is there. But with a little magic, we can figure it out. So here is the frequency response, and we can already see that there's far and away a point that, or a frequency that is present here, and everything else is just unneeded noise. So like I was saying in the last demo, we can just set our power spectrum density for as 1000 and zero out every other frequency. And I did just that here. This leaves a single peak somewhere here. Let's zoom in. and that is at 600 hertz. And what do you know? That's exactly the frequency that I was playing on my phone in the background. Moving back into the time domain, we can see what the signal should have looked like if there was absolutely no noise in the recording. And on the left here is the original, and on the right is what it's actually supposed to look like. So I hope you learned something. I hope you thought this was interesting. If you have any questions, just message me. Thanks for watching.